Hello, I'm Inseung Hwang from KAIST in Korea. In this video, I'll present our book titled Benchmarking Burst Super Resolution for Polarization Images, Noise Dataset and Analysis. Noise is a key challenge in computer vision and even more critical in polarization imaging. While unpolarized images appear clean with high PSNR, the degree of linear polarization images shows noticeable noise and color shift in single images. For the angle of linear polarization, the problem is even more significant. To address this, we analyzed the noise propagation in polarization images and built dataset with noise statistics. We first introduced the PolarNS dataset. It contains noise-reduced images with noise statistics. The dataset includes 54 objects captured in a dark room and 190 indoor and outdoor scenes. We collected 10,000 images per object in the dark room and about 1,000 images per scenes for indoor and outdoor captures. This dataset enables systemic analysis of polarization noise. Next, we propose the Polar Burst Tensor dataset, which provides polarization burst super resolution image pairs. It includes static burst GT and 14 sequences of handheld burst. These images were aligned and corrected to create a dataset suitable for training and evaluation of burst super resolution models. For modeling polarization noise, we used the shot and read noise model and extended it to stock spectra. We observed that each variance depends only on S0 component. For modeling DOLP and AOLP, we consider a bivariate normal distribution centered at the true value. Observed value can be plotted on a two-dimensional plane. Then DOLP can be described as the line integral of a circle. This can be expressed numerically as a Rayleigh distribution. When drawing a blue circle passing through the true value, the integral inside the circle is always smaller than that outside. Therefore, the distribution of DOLP is biased toward value larger than the true DOLP. AOLP can be described as the line integral of each direction. This can be expressed numerically as a projected normal distribution. To validate our noise model, we compared our noise model with data measured in a dark room. We can see that our noise model fit well with the measurement. To validate our data set, we compared it with other polarization dataset. As shown in the table, our dataset shows better noise suppression compared to existing datasets. We also provide estimated statistics of the physical values using our noise analysis model. As you can see from the plot, we significantly reduce the influence of noise by taking a large number of shots. These differences are even clearer in the table. In particular, the standard deviation of AOLP stays within 10 degrees in over 97% of cases compared to only 11% for single images. We benchmarked several state-of-the-art burst tensor models using our polarization burst tensor dataset. We compared RGB pre-trained models with models trained directly on our polarization dataset. The result clearly shows that polarization-specific training significantly improves performance across multiple methods. Looking at the example images, we can see that while RGB pre-trained models perform better than the raw input, the polarization-trained models consistently produce better results regardless of the network architecture. The difference is even clearer for AOLP. RGB pre-trained results differ greatly from the ground truth, which make it difficult to reconstruct accurate surface normals. In contrast, The polarization trained models produce its values much closer to the ground truth. To summarize, we present PolarNS and PolarBurst SR, the first dataset for polarization noise statistics and burst resolution. We proposed a noise model that quantifies polarization noise and its propagation across channels. Finally, we provide a benchmark study of state-of-the-art burst SR models in the polarization domain. For more detail, please visit our project page. Thank you for your attention.